Hi, my name is Paul Acchione. I'm a professional engineer with over 40 years of electrical energy sector experience. In this seminar, we will be discussing the challenges of integrating wind generation into the Ontario electrical grid. This seminar is taped, so you will not be able to ask questions online. We normally run the webinars live where you can ask questions. However, if you do have some questions about this particular seminar, feel free to visit OSPE's LinkedIn group and post your questions there, and one of the staff or myself will answer them in due course. Okay, so in terms of where we're heading, let's look at have a quick look at the outline. We'll be covering OSPE's role in policy advocacy. We'll be looking at why Ontario's wind generation is out of step with electrical demand, why wind generation is difficult to integrate into Ontario's electrical grid, why electricity market prices collapse and even go negative in Ontario, why Quebec's hydroelectric storage capacity is not available to Ontario in any major way, why wind generation results in higher greenhouse gas emissions in Ontario, why nuclear generation is needed if we want to achieve very low greenhouse gas emissions, and we'll look at the economic impact of load following, or what is often referred to as dispatching. The sources for today's presentation include the demand and generation data from the Independent Electricity System Operator. They have a website, and you can download data from the website, or you can request historical data that's not available on the website. And the IESO is more than happy to provide it to researchers or engineers who want to do their own analysis on the grid demand or generation data. However, you should be aware that the solar data is not yet available on the website, and that solar data won't be available till probably the end of 2014. Electricity production cost data that we present in this seminar is from the Ontario feed-in tariff rates, and also for nuclear and gas generation we use the cost of generating electricity 2010 edition from the OECD organization. We use the median case, and we remove the carbon tax since Ontario does not impose a carbon tax at the present time. You can also download policy documents in this particular slide presentation if you want to review it as a slide set from the OSPE website at the link that's provided there on the screen. Now, OSPE has an energy task force, and its role is not to do detailed engineering analysis, but to essentially identify problems that we see in the energy field, and in this particular case, electrical energy problems on the grid, and bring those problems and potential solutions to the attention of government and the agencies involved. And the reason we do that is primarily to help our engineers in the energy sector, and also engineers who use a lot of energy in their particular manufacturing or industrial sectors, since the reliability and cost of energy is a big component in the economic well-being in their sectors, and of course that ties into engineering jobs and job opportunities, which OSPE is very much interested in. OSPE is a non-partisan organization, and so we provide our analysis, recommendations, and other data to all the political parties who would like to see the data, and also to the various agencies and ministry staff. OSPE's role is not to do actual engineering or detailed engineering, but again to call attention to the policy issues that need engineering input, and hopefully the individuals responsible will take up the issue. We've had quite a lot of success the last 2 or 3 years working with the ministry staff, agencies, and stakeholders in getting some major changes to our market rules. In early 2013, nuclear power plants started to maneuver or load follow, as some people call it, to reduce their output when the demand is not needed. This started at the Bruce site in 2013 in February, and is expected to start happening at the Darlington site after the refurbishment program is executed on those units. Darlington has some additional changes to make to allow those plants to do that, and the task is a little larger than it was at the Bruce plants, and so the work will be done during refurbishment rather than as the plant comes down for annual maintenance. Now, in terms of the context of the presentation, the Ontario Green Energy Act was introduced in the mid-2009 period, and it changed the nature of electricity production. It opened up the electricity grid to private sector producers, particularly wind, solar, and other forms of renewable generation. It introduced the feed-in tariff program and rules. It created many design and operating challenges, unfortunately, because of engineering factors that were not fully considered during the development of the Act. Ontario has more baseload capacity than it can use. It has 11,000 megawatts of minimum demand every year, but over 17,000 megawatts of installed baseload capacity in 2013, and it's growing as we add more hydraulic and wind to the grid, since those are available in the evening, which defines the baseload demand. We've also returned the Bruce reactors to service because the government expected the capacity or the demand on the system to increase, but in fact the demand did not increase, in part because of the recession in the 2008-2009 period, and in part because of the higher prices of electricity are discouraging demand and encouraging more conservation. So we essentially have too much baseload demand for the system here in Ontario. The total demand on the system, even at peak demand in the summer, is only 25,000 megawatts, and the minimum, as I said, is in the spring, typically on a holiday weekend, of about 11,000 megawatts. Ontario has very little storage to absorb intermittent or variable sources like wind and solar generation. When we built our hydraulic plants, we did not add a large amount of storage like they did in Quebec. That was primarily to reduce the environmental impact of the hydroelectric facilities. But of course that means that there isn't very much storage in the system to be able to store and move these generation energy sources like wind and solar to periods of the day when we can better use that output. So flexible backup is needed to integrate the wind and solar generation. Storage is still much too expensive to build from scratch, and so most jurisdictions, including Ontario, are currently using gas-fired generating stations as the backup for wind and solar generation. Now, if we look at the demand in Ontario for a typical year, the chart that you see right now on the screen, the red curve is the peak. Throughout the year, you're looking at 365 days here. The ups and downs are typically weeks. there are 52 weeks in that chart and 365 days. The lower chart in blue is the minimum load typically in the evening. In the spring and in the fall, we have the minimum load at night. In the summer, we have the maximum peak demand. We also have a higher nighttime demand at night. Primarily, air conditioning is driving this summer peak, and winter heating is driving this winter peak in January and February. But the summer peak is the highest. Ontario is a summer peaking grid, and so we need some peaking capacity to be able to meet that variable demand. We typically use solar, daytime wind, flexible nuclear, flexible hydraulic, flexible combined heat and power and bioenergy, and flexible natural gas to cover the peak demand. And for baseload demand, which is typically at night, we use natural gas that must run and is needed for spinning reserve, must run hydraulic. These are run-of-the-river plants that can't be shut down. Must run nuclear. These are the inflexible plants like Darlington and Pickering, and the portion of inflexible nuclear at the Bruce site. The flexible portion at Bruce can be used for peak for managing the peak load. Must run combined heat and power plants is also a base load, and of course nighttime wind arrives during that base load period. Now, if we look at one of those days on that chart that's squeezed in into that chart, we'll notice that in the lowest demand day, which is in the spring, we see that roughly 11,000 megawatts in the early hours of the morning. We see the peak in that spring period. The green, by the way, a chart here, the green graph is the Ontario load. The dotted red line is the total load, which means in this particular example we're exporting a considerable amount of power into the adjoining grids. And the black dotted line shows you what that daily baseload demand is. The baseload is defined as the minimum during the evening hours. And the baseload plants will operate throughout this entire 24-hour period, typically at full load. And this distance between the dotted line and the green line is filled in by the peaking plants. And the distance between the green line and the red line is filled in by available generation that can be used to export when there's an export demand. And we can get a price for that power which exceeds the fueling cost of the plant, so that we can recover some of our fixed cost on those plants by exporting the power at above the fueling cost. Now, keep in mind that if you have excess generation, you would not build a plant that you intend to use to sell power at slightly above the fueling cost, because that would not be economically viable. You would build the plant because of your own needs, and then when it's sitting around, you would be happy to use it to deliver export power when you can get more than the fueling price, so that you can reduce the fixed costs of that plant. But you certainly wouldn't build a plant to export power at lower than the total cost of production, and above, even if it is above the fueling cost, because you would be losing money by building that plant. In the summer, on the right side of the graph here, the same thing. The dotted line is the base load in the summer, typically around 17,000 megawatts. The peak demand is the green in Ontario, typically around 25,000 megawatts, and the red dotted is the total, including the exports. And Ontario typically now exports every day, every hour, all year round, since we have excess generation that is relatively low cost on fueling, and so it's worth our while to actually sell into the market all the time if we can recover our fuel cost plus some of our fixed cost. The typical peak in the summer is in a hot, sunny, windless day when we have the largest demand. And by definition, since the highest demand typically occurs when there's no wind to cool buildings, that means that wind generation really is not too helpful in meeting our peak demand in the summertime. Unfortunately, that's one of the problems with wind generation, is when you need it most. Most of it is not there. Now, wind generation does not align with demand in a number of ways and a number of other aspects. Because Ontario's proximity to the Great Lakes, wind is primarily driven by the solar cycle and associated weather patterns. It isn't driven by the ocean weather patterns. We're much too close to the Great Lakes, and they dominate the weather pattern. So wind tends to go up and down pretty much every day unless a large hurricane is traveling through the area. Wind is highly variable in Ontario. We'll look at the chart shortly. Wind is strong at night typically when demand is low. Wind is strong during the spring and fall when demand is low, and wind is weak in the summer when demand is highest. So these are not great engineering production properties, and that means that when we integrate wind into the grid, it is very challenging and somewhat more expensive than, for example, integrating solar, which happens to arrive when we need the power the most, typically in the peak. So wind is definitely a challenge to integrate it. Now, if we look at the seasonal variation in wind, and what you're looking at here is the total amount of wind generated in each hour of the day throughout the year. The black is the total. And as you can see, in the early hours of the morning when people are making breakfast and getting ready for work, having a shower, wind demand is typically lowest. And at near the end of the day, at 11 o'clock, 10, 11, 12 o'clock at night, when people are heading to bed, wind demand is highest. Not exactly the pattern that most people demand their electricity for. Now, down at the bottom of the chart, you'll see the various seasons. Dotted blue is winter production, the orange is autumn, green dotted is spring production, and red dotted is summer production. You'll notice the summer demand, which is the highest, produces the least amount of wind. And although the winter demand is respectable and the wind production is respectable in the wintertime, it also has a considerable amount of production in the spring and the fall when our demand is very low. So spring and fall is a challenge. We have too much wind to deal with at the wrong time of day, and also in the summer when we have a huge demand, the wind is not there to help us. Right. Now, these are the charts for wind production. The one on the left is typically the lowest demand week in the year. The one on the right is the highest demand summer peak. If you take a look at the spring low demand period, the red lines are the daily production requirements demanded by the customers. This is percent of the 100% summer peak load. So typically in the spring we're running at about 65% demand during the day and around 50% demand at night. And yet wind, as you can see, can rise up in the spring. In this particular week, it got up to almost 80% output. So we would have to spill that energy, or as we say in the business, dispatch wind down, to prevent it from accelerating the frequency on the grid or pushing power into our neighbor jurisdictions and violating our energy transfer agreements. So, and of course, if you look at midweek here in this particular example, wind was not available for a good chunk of the day here in the middle of the chart, when demand was not only high at night, but at a respectable level at night, around 50% of total system demand. But even the peak here on Tuesday, asking for 65% of total system demand, and wind is down around 15%. So that needs to be filled in by the backup energy source. Otherwise, you'll have a loss of voltage and a potential blackout. On the right-hand side, if we look at the summer peak, you can see that that there's a considerable reduction in the amount of wind available, and there's a huge area of low production here in this particular case on Tuesday, Wednesday, but demand is still quite high. That all needs to be filled in by the backup source if we had a grid that was made up of just wind and the backup. And that is pretty much one of the big challenges of wind is, as you can see, production isn't terribly aligned. And if you look at this particular peak demand week on the right, the highest wind production, which turned out to be about 60% on the Thursday, is coincident with the lowest demand at night. So your best wind happens to occur more than not during the evening when the system is actually down at the low point, not the high point. So not a particularly favorable production profile for power design engineers that have to integrate this stuff into the grid. Now, wind generation also drops below total 10% of total capacity across the province, approximately 20 days a year. At least that was the data for 2011. And it lasted for more than 24 hours. In other words, most of the wind capacity needs to be backed up by the backup source. It disappears for an extended period of time, too frequently in the year, to be able to consider it a dependable source of energy. It's basically an opportunistic supply. When it's available, you take it if you can, but when you need it, it's generally not there. By 2021, Ontario will have about 7,500 megawatts of wind turbines. Essentially, if we consider that they're about a megawatt each, although they vary in size from about a half a megawatt to 2.5 megawatts, instead of having 7,500 wind turbines that are operating independently of each other, what we really have in Ontario, because of the way wind is distributed throughout the province, at least the parts of the province where we have windmills, we really have one super large 7,500 megawatt wind turbine by the time all the wind is installed. Now that means that essentially you need to have almost 100% backup for wind in Ontario because of its production characteristics around the Great Lakes. That was something that was unexpected by the original planners of the Green Energy Act, and in fact by the industry itself that suggested to the government that there's wind blowing somewhere in Ontario all the time. Well, the data is now in, and for where the industry put their wind turbines, based on the locations where those turbines are now located in Ontario, a good number of days there is no wind for the whole day, and that means the backup has to be there for almost all of the capacity of wind turbines you put in. Now that means the reserve capacity is quite high for wind. It means that wind capacity in Ontario is essentially not a dependable primary source. It is a displacement source of energy. In other words, it displaces the energy provided by the backup system that needs to be built to handle wind in the first place. And that changes the economics of wind dramatically. You cannot take credit for the entire total cost of wind production. Wind is essentially got an economic value of the deferred costs of the backup, and in most cases, if the backup is clean like hydroelectric, it's only worth the fueling cost of hydroelectric. And in the case of gas, you have the fueling cost of gas, and of course the greenhouse gas emission value, since gas does have greenhouse gas emissions which have a negative impact on the environment. But gas is 60% cleaner than coal, So you don't get a lot of value for wind in Ontario because we've decided on a policy basis to eliminate coal. And the best value for wind is when it displaces coal generation. And of course, since we got rid of coal, wind is now displacing gas, and it has only 40% of the value environmentally when it displaces gas compared to displacing coal. The US, Europe, and China have very large amounts of coal generation, and so when they install wind capacity in those jurisdictions, they are getting a lot better value for their wind generation than we do here in Ontario. Now, this backup problem for wind, what it really means, as I said, is that wind is a displacement energy source. If we look at the fuel that we displace in the various times of the day, when we displace, when wind is displacing gas, it's displacing energy at around 3 to 4 cents in fuel cost. For gas at the present price of around $3 to $4 per million BTUs, the current price on the market. We can maybe double that if we look at the long-term price of gas, since a lot of the suppliers will blend their short-term and long-term prices for gas. They do some hedging. If it's hydroelectric or nuclear that provides the backup or that we're displacing, it's only worth about ½ cent per kilowatt hour. And then, of course, there's the CO2 emissions. In the case of gas, there are CO2 emissions, and there's about 400 kilograms per megawatt hour or 400 grams per kilowatt hour of emissions. And depending on the value of carbon emissions, it will have a value. Typically, if you're looking at about $30 per ton of CO2, that represents about 1 cent per kilowatt hour in the case of gas. Coal, it would be closer to about 2½ cents. And some environmentalists think a better price for the impact of emissions is closer to $100 per ton. If you use the $100 figure, it works out to about 3.5 cents for gas, and about roughly 10 cents for coal. So as you can see, if you're displacing coal, wind does make economic sense. But if you're displacing gas, it's hard to make a case for wind when you're paying 11.5 cents for wind, and you're only benefiting from 3 to 4 cents on the fuel, and roughly 3.5 cents on the greenhouse gas emissions. Doesn't make up enough of a savings to pay for the wind at the current fit rates. However, if you are in a jurisdiction with lots of coal, or even worse, if you're in a jurisdiction that burns the brown or lignite coal, which is even dirtier than regular coal that we use here in North America. For example, China and Germany use a lot of lignite. It's about 10% dirtier than regular coal, so you get even more value by putting wind on the grid in those jurisdictions. Unfortunately, Ontario has no coal right now. As of the end of 2014, will be coal-free. The feed-in tariff rate for wind, as I said, was 11.5 cents. So when you do the math, it comes out to about 4 times its daytime value and about 23 times its nighttime value, based on fuel alone. And by the way, that's not including the transmission upgrade costs, which are required for wind, because remember, wind has a capacity factor of about 29 to 30%. Which means the transmission lines from the main bulk transmission system to the wind farm only operates at 29 to 30% of its capacity factor. So you're putting in a lot of transmission line and supporting facilities that only runs less than 1/3 of the time. So that increases the transmission costs per kilowatt hour for that portion of the expense, and that's not included in the fit rate. In many cases, The high premium for wind energy then causes our global adjustment mechanism, which is built into our electricity prices, to rise, which then of course increases the cost of electricity to both consumers and businesses. And in the case of businesses, since they're paying for the electricity in their bill every month, it's driving the cost of their goods and services up, which puts them at a competitive disadvantage in the NAFTA, North American Free Trade Zone. And this is a concern we have here at OSPE, because it affects not only general economic conditions, but since most engineering jobs are derived from economic activity, either from manufacturers or industrial concerns. If they lose their competitive advantage, it affects engineering jobs quite dramatically. Now, wind is difficult to integrate, as I said, because of its production characteristics are incompatible with the demand characteristics. But we also have the two problems that I mentioned earlier, is that our baseload plants, especially nuclear, are rather inflexible. With the exception of Bruce Power, which is now maneuvering since February 2013. But even Bruce can only maneuver about a third of its output. The bottom two-thirds of its output is inflexible. And of course, Ontario has very little storage and no seasonal storage to speak of. Seasonal means enough storage to carry you from the spring high production in wind to move that to the high demand summer period, and from the high wind production in the fall to the high winter demand period. That type of storage requires quite a lot of hours of storage, and it's just simply not available in Ontario. So the poor alignment of wind production with demand, combined with inflexible nuclear and the lack of storage, makes integrating wind, as I said, both difficult from an engineering perspective and also costly from an economic perspective. Load demand has not grown as much as predicted, and unfortunately we've been adding base load capacity because we thought the demand was going to grow, since these plants are typically ordered and contracted for many years in advance, because it takes time to do the environmental assessments, the construction and commissioning. The conservation programs are causing the nighttime load to drop, because typically nighttime load is easier to shed from your demand than daytime load. It's easier to turn things off like night and not to air condition or heat your homes as much in the evening when you're not using the facilities as extensively as we do during the day. Air conditioning loads are causing, unfortunately, the peak load to rise in the summer. In part, this is happening because we charge more for nighttime demand than it costs to produce it. Our nighttime charge for power is higher than the baseload cost of running the baseload plants, and during the day we're charging much less for peak power than it costs to produce peak power. So we're actually discouraging people from using nighttime load, which we need to keep the baseload plants operating efficiently, and we're encouraging additional air conditioning and peak load during the day, which we really would prefer to not have, because it's so expensive to produce peak generation. But that's unfortunately the result of our pricing model in Ontario is not as well tuned as it should be to the needs of the grid from an engineering point of view. It's been designed to try to make consumers a little more comfortable with the electricity rates, but it's not helping in terms of smoothing out the load on the grid. It's actually making it worse. California has a much more differentiated price between night and daytime, and a lot of the smart grid ideas that are being developed in our research labs, in fact, are finding some markets in California where the price differential between daytime and nighttime is much higher than Ontario, and you can save some money by shifting your load, and a lot of those new technology products are in fact finding a home in California, but not yet in Ontario. Just can't save enough money in Ontario to purchase that equipment. Grid operating capacity factor, as I said, now if we look at that chart we saw earlier for the whole year, is at about 63% capacity factor, which means 37% of our grid assets are underutilized. Now we have too much baseload capacity as a night, as I said, and weekends, especially during the spring and fall. Now some of this can be managed by scheduling our outages on our baseload plants, and they do that, but not all of it can be managed that way, and so we're forced to export a lot of that baseload power at below the total cost of production, above its fuel cost, but again below the total cost of production. So we're not able to recover all the fixed costs for those plants that we've in fact overbuilt the last few years because of that that recession and some conservation programs that have lowered well, it hasn't actually lowered the demand. It's pretty much flat over the last several years, but the demand did not rise as expected when the system was planned for a few years back. So we're in the fortunate or maybe unfortunate situation of having too much baseload generation on the grid. Now, one of the things that's been really surprising to a lot of people is why electricity prices can collapse and go negative. The reason for that is the way we have designed our auction market for electricity in Ontario. We require all the plants to bid into the market, and the last plant to be added to the grid to meet the total demand sets the market price, and that clearing price is then paid to everyone who has put in a lower bid. What that means is that if somebody wants to run or has to run because they can't shut their plant down, in the case of a baseload nuclear plant or a run-of-the-river hydraulic plant, they will bid a very low price into the market to make sure they're picked to run, and they allow the gas plants or other plants to set the price. But if the demand on the grid should fall low enough that even the baseload plants are not required, then those very low prices that are bid by the baseload hydraulic and nuclear plants will actually be picked up in the auction, and they will set a very low negative price. Now, the more that these baseload plants can maneuver, the better, because then we won't have to put in, or the bidders won't have to put in such very low negative prices to ensure that they're not shut down during the auction market bidding process. And in fact, when the Bruce plants started to maneuver in February 2013, and subsequently in September 2013, when solar and wind began to be dispatched down when we could not use the power, the grid has subsequently run much better. There's very few days now where we have very deep negative prices. But the dispatching points for nuclear, flexible nuclear, and the dispatching point for wind and solar are a slightly negative energy price, which means that we have more frequent days now where we have a slight negative price. And that, of course, encourages exports, which drives energy out of the province. And so these plants don't have to be shut down, which is good. The problem, of course, is that we're not getting much of our fixed costs recovered if the energy price is close to zero or negative. The average price for the wholesale price for electricity in the auction market last year in 2013 was about 2.65 cents per kilowatt hour, yeah, as you probably know, that's not enough to pay for any of our generation at its total price. The total price for hydroelectric varies from about 3.8 to about 12 cents depending on the plant. I think the average price last year, if my recollection serves me right, was about 4.8 for hydraulic, about 6 for nuclear. So even hydraulic plants cannot make money on the wholesale price in Ontario. And so the government has had to introduce the global adjustment to pay people for their contracted power at the rates that were guaranteed when the contracts were signed. So virtually every plant now has to be paid out of the global adjustment because the wholesale price is so low because of the surplus generation that there is not enough money in the wholesale market to pay all the bills that have been that have to be paid as a result of the contracts that were signed when the plants were committed a number of years ago. Nuclear plants have a huge shutdown cost if they do come down, and that's why the inflexible nuclear plants tend to bid very low into the market, so they don't incur this 3-day shutdown if they come down, because once they're down, there's some reactor physics isotopes that build up in the reactor core, and you have to wait till they decay away before you can restart the plant. So typically, if a nuclear plant is shut down, it's down for 3 days before it can get back up. So it's a very high cost shutdown, and the nuclear plants that cannot maneuver generally bid very low price into the auction market to make sure that they are not shut down. During very low demand periods with strong wind, this can result in a very large negative market clearing price. And so in order to avoid that, now the dispatch rules were changed in 2013 to force wind and solar down if the price goes negative. I believe wind and solar are being dispatched now around at approximately -1 cent per kilowatt hour. So if the price falls, the market price falls below that, then wind and solar are told to shut down and reduce their output. And that keeps the market price from collapsing to the very low values, unless all the wind and solar are shut down, and then the very low nuclear and hydroelectric prices are reached, and those bid prices typically are very deep negative prices, and then the power is exported at a very significant loss to the Ontario consumers. So it's really important in the grid to have sufficient flexibility that you never reach those must-run hydroelectric or nuclear units that cannot be shut down. Otherwise, it hurts financially on the export of that energy. Now, as I said, the dispatching rules for nuclear at Bruce site, at the Bruce plants, and wind and solar in 2013 have made a very significant improvement to the both the economic and the technical performance of the grid since the end of 2013. Now, another odd question or another odd fact that a lot of people don't understand is why can't Ontario access the Hydro-Quebec storage pool in James Bay, in the James Bay area? Hydro-Quebec has an extensive storage system up there, but there are technical and economic reasons why Ontario has not been able to negotiate a deal to access Hydro-Quebec's storage facilities. It would be a great marriage if we could get it, because the excess wind and solar, when we can't use it, or the excess nuclear, could be stored by holding back the water at the Hydro-Quebec dams, and then later on the next day we could allow that power to flow back into Ontario for the peak. But here's the problem. Ontario, to handle about 10,000 megawatts of wind and solar generation, would need in the neighborhood of about 7,000 megawatts of storage to effectively integrate that into the grid based on our back-of-the-envelope calculations at OSPE. The present tie lines to Quebec are limited to 2,000 megawatts. Now, we're using these lines as best as we can, but certainly they're nowhere large enough to handle 7,000 megawatts. You would need another transmission corridor the size of the one that you see going along the Highway 407 north of Toronto, and that would run from our major load center in the GTA all the way up to James, close to James Bay. So it's an extensive transmission corridor, very difficult to get public acceptance of something that size, and also very expensive. In addition, we have to remember that we want to store the energy at night when it's produced and we don't need it, and that's not a problem for Hydro-Quebec. The problem is that we want it back when we're at our peak demand, and typically that's also when Quebec has their peak demand during the day. They have a winter peak, we have a summer peak, so there's a little bit of room there to share, but not an awful lot, because their summer peak is still quite high, and as they add more air conditioning, their summer peak will continue to rise. So the problem is their dam capacity at the moment has been sized for their peak, and they don't have the additional 5,000 megawatts to deliver Ontario its stored energy during Ontario's peak without increasing the capacity of those dams. So we're talking of tens of billions of dollars in transmission and generation upgrades. And while Hydro-Quebec, I'm pretty sure, is prepared to do that if Ontario pays for it, Ontario has found that the cost of using Hydro-Quebec storage is prohibitively expensive, and it's cheaper to actually build the storage here in Ontario. Now, while it is cheaper to build the storage here in Ontario, when you run the numbers, storage is still much more expensive than gas backup, and with the low gas prices at the present time. And so typically most jurisdictions now prefer to use gas backup for wind and solar rather than to use storage. Now the problem from an environmental point of view is that produces greenhouse gas emissions of about 400 kilograms per megawatt hour. It's not emission free, unfortunately. Storage would be emission free, but storage is so expensive that most jurisdictions are steering clear of it right now until the technology improves and the prices come down substantially. Very short-term storage, less than 1 hour, is starting to become economic when you do both storage and voltage control, because you can defer the expense for voltage control equipment if you use the storage equipment to do that. So very short-term storage is now starting to become economic at the distribution level, but transmission level grid scale storage for moving energy from spring to summer and fall to winter is still prohibitively expensive, and so gas backup is still the choice that almost all utilities make now when they bring in wind and solar. They actually add gas generation to the mix when they do that. Now, the additional wind generation can increase greenhouse gas emissions for that very reason. As you add wind and solar, and you need more backup capacity that's very flexible, gas plants are the most flexible generation sources we have. And so typically when you add wind and solar to the grid, unless you have extensive storage facilities, which some utilities do, but certainly not here in Ontario, then Ontario is pretty much stuck with adding gas backup, and that means adding wind and solar to an electrical grid like Ontario's, which is primarily nuclear and hydroelectric, which is zero emitting with no coal, means that when you add wind and solar to Ontario's grid, you actually drive GHG emissions up. Now that was studied not only by OSPE, but also by the independent electricity system operators who have confirmed our own calculations. And typically, if you're forced to shut down nuclear plants to make room for wind, then you have to back up that wind with gas when the nukes are shut down and waiting to be restarted. That bill alone for that nuclear shutdown strategy adds about $200 million of fuel costs to the system and about just under 2 million tons of CO2 emissions. That's a 2014 estimate, which is not the largest amount of wind and solar capacity that's planned. So it's a strategy, unfortunately, that is not a low GHG emission strategy to add wind and solar to Ontario's grid. because Ontario's grid right now operates at extremely low emission levels because of its 80 to 85% hydroelectric and nuclear capacity, which has essentially zero emissions. Now, if you do the math, as I said, because of this need for gas for backup, and because of its emission properties, when you do the math, since there's limited hydroelectric resources that are economic in Ontario, the only way you can achieve low GHG emissions, typically below about 150 grams per kilowatt hour, is to rely more on nuclear for your base load and rely on your gas backup only for your peak load. The problem, of course, that we have is there's a lot of public resistance to additional nuclear capacity for a number of reasons. But from an engineering point of view, you cannot get very low emission levels without hydroelectric or nuclear. And right now Ontario produces electricity at around 80 grams per kilowatt hour or 80 kilograms per megawatt hour of CO2, and it's one of the cleanest emitting one of the cleanest grids, lowest emission grids in the world, other than the pure hydraulic grids like Quebec or the heavier nuclear grids like France, where they rely more on hydroelectric or nuclear than Ontario does. So that's the unfortunate or inconvenient truth with the math. Engineers can do a lot with their engineering knowledge, but they can't change the laws of mathematics or the laws of physics. And adding wind and solar, unfortunately, to Ontario's grid right now, because storage is so expensive, results in more gas burn, and that means wind and solar are really not low GHG emission strategies, at least not in Ontario. So, as I said, solar has a 13 to 15% capacity factor. Wind has a 30% capacity factor, roughly. Since the grid has a 63% capacity factor, then if you were to take a wind gas-powered grid with no other sources, you'd have about 200 kilograms of CO2 per megawatt hour. For a solar and gas-powered electrical grid, you'd have about 300 kilograms of CO2. And Ontario, as I said earlier, is currently operating at about 80 grams per CO2, kilograms per CO2 per megawatt hour. So Ontario is already achieving emissions much lower than can be achieved with a wind or gas solar grid. If you combine wind and solar together with gas, you can probably get that down to about 150 kilograms per megawatt hour. But again, that's still much higher than we're producing now. And in fact, if you look at the energy plan, Ontario's recent 2013 energy plan, it shows GHG emissions between 2016 and 2032, I believe, doubling as we reduce the nuclear capacity with Pickering going offline, and we increase the gas burn as wind and solar are added to the grid. The gas, of course, is for the backup. So even the Energy Ministry now has confirmed what OSPE has been saying, is that wind and solar with gas backup is not a low GHG emitting strategy. Now, the economic impact of load following or dispatching. Now, when you when customers don't demand the power, you have to reduce the amount of generation. But the problem, of course, is that then your fixed costs are not covered if the plant is not running. People, unfortunately, don't understand the difference between the energy cost on a per kilowatt hour basis and what we refer to in the engineering discipline as the levelized cost of electricity. or LCOE, which is the total cost of production divided by the total energy produced by the plant over its lifetime. And that's the number that's used to decide whether you build or don't build a particular plant when you need more capacity. But the capacity factor that the plant operates has an enormous impact on the LCOE, or the levelized cost of electricity. And LCOE is not the wholesale nor the retail price. The wholesale price is the HOEP, or the hourly Ontario electricity price, and the retail price that you typically pay, or consumers typically pay, or small businesses typically pay, are the TOU, or time of use prices or rates. As I mentioned earlier, the retail prices actually charge too much for baseload energy and not enough for peak load energy, and this creates problems in trying to flatten the load profile so that we can make better use of the grid capacity and get our average cost of power down and our rates down. So this is an area where OSPE has been talking to the ministry about changing the way we price electricity. In fact, we have another seminar on a smart grid electricity price plan that we think will incent customers to adopt some new technology that we're developing here in Ontario. But the current market prices for electricity, the way we sell electricity, does not generate enough savings for these products to be sold in Ontario. So many of these products are having to go to other markets to find a market for them, such as California and other places that charge much higher rates for peak power. So anyways, energy policies are really important if we want to improve grid capacity factors and lower electricity costs and reduce our greenhouse gas emissions. If you get the energy policies wrong, or you don't understand the math that drives the costs, you could very easily end up driving costs up, emissions up, when we add a new generation that on the surface sounds like it's cleaner, but in fact results in higher cost and higher emissions, as we've discussed just a few minutes ago. So here's what happens to the cost when you start dispatching or turning off these things. And now we're dispatching solar, wind, and nuclear, and we're doing a bit of dispatching on hydraulic also. We're spilling water at Niagara when it's really low demand and we can't get rid of the power through our neighboring grids. If you look at the yellow curve, this one is for solar. It comes in at around 28 cents for the fit rates at on the ground solar farm. But if you cut the amount of power that's available from those panels in half by dispatching it off half the time, you could double the price up to around 56 cents very quickly, because solar only has about a 13 to 15% capacity factor in Ontario. So if you lose roughly 7.5% of its capacity out of 100 through dispatching, you double the price of solar. So you really do not want to dispatch solar unless you absolutely have to for technical reasons, because the cost goes through the roof very quickly. Wind is the next one at 11.5 cents. You can go to 22.5 cents by dispatching it half the time at 15% capacity reduction from the 30% nominal, and it continues going up if you dispatch it even further. So again, solar for sure, and wind, the next one, very sensitive to dispatching, and so you try to avoid as much dispatching for those two sources as you possibly can. And in fact, they're the last to be dispatched in our rules. Solar and wind get dispatched after nuclear and after gas, for that reason. If you look at nuclear, which is the orange or red here, it has a steeper curve near the end when you're getting to the point where you're not using much of the power. But you can half the output from a nuclear plant, and its cost will go from roughly 6 cents to 12 cents when you drop capacity utilization in half, which is about 42% dispatch, which is right about here where it crosses these blue lines, which are the gas lines. But as you can see, you can dispatch nuclear quite a bit without affecting the per unit price of electricity as much as solar and wind, but it is more sensitive than gas. And the reason for that is that gas, when you don't run it, you don't burn the fuel, whereas nuclear, if the plant is running, the fuel is still being consumed and you have to dump the energy either to the turbine condensers or to separate steam bypass condensers. Our reactors currently aren't designed to reduce output by reducing reactor power. And even if they were, most of the cost of nuclear is capital, so these lines tend to be steeper than gas anyway. Most of the gas prices is fuel, typically about 60% or 70% of the cost of running a gas plant is fuel. And if you're not burning the fuel, that means these lines are very flat, and the four lines you see here all the way from $4 at the bottom per million BTUs up to $16 per million BTUs. The price for gas in North America is about $4 on the spot market, roughly about $8 on the longer term market. And in Europe it's about $12. In Japan and China I believe it's closer to $16 per million BTUs. So these four lines give you some idea of the global energy price for gas throughout the world, and it shows you where gas fits in with nuclear, wind and solar, not only if you use all of their energy at the zero dispatching point, but as you start to dispatch these plants, how these costs vary. And as you can see, the more expensive plants like nuclear, and although it's not shown here, hydroelectric, are so capital intensive that you really would like not to dispatch them either. In fact, you don't want to dispatch any of the high capital cost sources because they have high fixed costs, so you want to run these as much as you can. So solar, wind, nuclear, and hydroelectric, you really would like to run them flat out if you can and use gas for peaking. That would give you the lowest cost system. The minute you dispatch solar, wind, and nuclear, you drive costs up, which is what's going to happen over the next couple years as these sources have to be dispatched because we've got too much base load generation. And some days in the spring and fall we have too much peak generation because the solar actually comes in more than we'll need on certain days because the baseload plants can't back down far enough. So in summary, we need to include engineering considerations into the development of energy policy. If we don't do the math and we don't consider the production characteristics of each of these sources compared to the demand characteristics of the customer demand, then we run the risk of having a lot of that energy either dispatched off or sold at very low prices, which means we're paying more of the fixed cost into our individual bills here in Ontario, both for industry and for consumers. So we drive up the cost of electricity needlessly. We need to better integrate them, of course, to avoid wasting their environmental benefits. If you're dispatching wind and solar and nuclear, then you're dispatching zero emission sources and you're burning more gas when those sources aren't available. So you're not getting your best value in terms of environmental benefits if you're not making best use of the wind, solar, and nuclear and hydraulic. In the longer term, we need to manage the demand a little better by using smart grid technology. We can shift the load. We can do some storage. Thermal storage is cheaper than electrical storage, so there's some things that we can do with thermal storage to move some of our air conditioning and heating loads into the evening rather than during the day. For example, we could subcool buildings during the night in the summer and heat them, preheat them at night during the winter to try to remove some of that daytime load and rebalance our grid. But that requires smart controllers, and that's technology that needs to be purchased. And currently, if the price signals on our rate structure do not save you enough money, then you're not going to invest in that technology. So we really do need to look at not just demand management per se, but also our pricing structure to encourage people to take advantage of some of these new technological improvements that are being developed at our R&D labs. We need to that balancing of the grid load will help to better utilize the current assets, which means that we can get future growth in the system without spending any more money on new generation capacity. So over time, the rates will come down by the extent to which we improve the grid utilization capacity from the current 63% to some higher value. Improving nuclear flexibility, such as load falling, will reduce greenhouse gas emissions, because then nuclear can start to provide some of the backup, not all, but some of the backup for wind and solar when nuclear is available, and that way we won't have to burn gas for a portion of that period when the wind and solar needs to be backed up. And of course, storage. Hopefully the technology will help reduce the price of storage. Currently, very short-term storage under an hour is now starting to look competitive when we combine it with also voltage regulation at the distribution level. And hopefully over the next several years, as technology improves and costs come down, we can start to increase the amount of storage so that we can start doing daily storage. That would be a big help. Weekly storage for the weekend, and at some point down the road in the future, maybe we can do seasonal storage, which then would allow us to use renewables and nuclear in the most efficient way possible. So that's for the future. Now we won't be able to take questions online because this is a taped presentation. I hope you've enjoyed it and learned something from the seminar. And we hope that you'll catch some of our online live seminars in the future, and some of these will be taped and put online so that you can view them at your leisure at a future date. The slides are also available if you want to read them a little more carefully at your own leisure, or if you want to use them to do presentations to your own technical or community groups. You're more than welcome to download the presentation material, and if you feel comfortable delivering those to your communities and or your colleagues at work or in your various engineering associations, you're more than welcome to do so, as long as you use the slide pack that OSPE provides and acknowledge OSPE's contribution to their production. Anyways, enjoy your day, and as I say, I hope you had a fruitful time with the seminar material. Thank you very much.